All righty, welcome back, everybody. Let's go ahead and get into it for today. So we're going to be starting today talking about molecules and ions. So of course, molecules, we've already been kind of looking at them. These are going to be collections of atoms. Molecules will have a specific structure, a specific shape, um, and they will perform specific chemical interactions. So here in many different ways on this slide, you see the phosphine molecule. I picked that because it's an interesting molecule, especially for exobiology. Phosphine is a molecule that's difficult to make on rocky planets. So when you find it in the atmosphere of an exoplanet, you're looking at a good chance of anaerobic life forms uh, on that planet creating this molecule. So it's one of the ways that exobiologists look for the possibility of life on other planets. But you see multiple different ways for it to be represented. First off, you see phosphine's molecular or chemical formula, pH3. So of course you have your phosphorus up here. Each one of these is a hydrogen. But the different ways you can see a molecule represented is the top left here is the ball and stick model. The bottom left is called the space filling model. And you have explanations for these in your book, but uh, just kind of be pairing those with these images. The space filling model is supposed to be showing the relative sizes of the atoms in the molecule to each other. On the bottom right, you see two types of Lewis structures. And we'll get into that more as time goes on. But the Lewis structures are going to be basic representations of the atoms, bonds, and electron placement inside of a molecule. So the first Lewis structure on the left is a very standard one, where you're really just drawing in the bonds and the connected atoms uh, kind of in a square pattern. The one on the right is something, again, we'll get into as time goes on, where the phosphine is in its proper molecular geometry. And so, of course, here you see three-dimensional representations where your wedge is a hydrogen coming out at you, and your dashed line is a bond to a hydrogen going back into the screen. But that's going to be that's going to be we'll go into that more deeply. Yeah, it'll work. We'll go into that when we get into molecular geometry. So what we want to start by talking about covalent bonding. So first off, what you're seeing up here in your Lewis structure is a covalent bond, covalent bond, covalent bond. These right there, that's a covalent bond. And what a covalent bond is when two atoms share electrons. And when they share electrons, then each atom gets both of the electrons in the bond uh, into its own orbitals or electronic structure. So let's kind of look at what this looks like. If you look up here at the top left, you see atom one and atom two, they're coming together. And so then what's going to happen is this electron and this electron are going to end up sharing, and you're going to get this covalent bond where A will get both of these and B will get both of these. And so the way we're more used to representing that is in our Lewis structures, each one of these little sticks is a covalent bond. And start wrapping your mind around the fact that each one of these little sticks, what would be, is two electrons. So every time you see a stick, you get two electrons. So like later on, when you have the nitrogen molecule, you see a triple bond, three sticks in between the two nitrogens. And each one of those gets two electrons. So that'd be 2, 4, 6 electrons in that triple bond between the two nitrogens. Something else you'll notice on your Lewis structures Again, introduce stuff early so that you can start getting used to the terminology, and we'll just go into it deeper and deeper as time goes on. These Lewis structures also have these little, these little dots up in different places. So that's going to be a lone pair of electrons. Lone pair electrons are electrons that still belong to that atom in particular, and they're not involved in bonding. So we'll go into that deeper as we start talking about valence electrons and we move forward with that. So here, of course, you see water, and you know that the molecular or chemical is low. So you can start comparing the Lewis structures and the Lewis structures and the various ways you might see a molecule to its molecular formula. This can get a little more complex as we start talking about ions. Ions are going to be, we're going to start with ions that come from elements. And so then it starts out as a neutral atom, and it will either gain or lose electrons to take on either a positive or negative charge. So, and we'll talk about the charge each ion is going to take as we look at the periodic table. Anions are, of course, negatively charged. Cations are positively charged. And so let's look at here, this top one, we see fluorine. So here, on the left, you have a neutral fluorine, so no charge. But what happens is the fluorine gains an electron, and it becomes the fluoride ion. Your elemental anions, whenever they become a negative ion, they will they will take the root of the word, the name of the element, and add IDE as its ending. So fluorine becomes fluoride. And so here, if you look, well, what's the charge on? I mean, so of course you see the minus up in the top. If you see just a minus or just a plus, a minus is a -1, a plus is a +1. So we don't put +1 or -1, we just put plus or minus. But now what we see here is you see protons and electrons. And so, we talked about protons as +1s, electrons as -1s. So if we look at a general equation for turning this fluoride into an ion, your fluorine plus the new electron is going to give you the fluoride ion. And so what we see is there's 9 protons. That's going to equal +9. So that's 9 times a +1. And then there's 10 electrons. When you have a -1 10 times, you get a -10. So the overall charge of the ion, 9 minus 10, is a -1. And down below it, you see magnesium. Magnesium becomes a positive ion or a cation. It does not change its name. So that's just the way you name these. This is just magnesium ion. So your anions will change their names. Your positive ions will not. But what you see happening is magnesium. There's that. It's going to lose 2 electrons. And so what you see, well, I have 12 protons. So 12 protons, +1 12 times is a +12. And I have 10 electrons, which is a -10. So 12 minus 10 is a +2. So that's the charge on the magnesium ion. And of course, you can see the original atoms are neutral because you see, like here with magnesium, 12 electrons, 12 protons, they're equal. So that's going to be +12 minus 12. That'll be neutral. And again, when I'm talking about neutral, I'm, just for now, I'm putting that little 0 up in the upper right-hand corner. That's where that's where you will represent charge. but we're not going to do that for very long. It's not a proper notation. If we look at a generalized chemical formula for this, for the magnesium ion, we get magnesium becomes magnesium 2 plus, and it gave off 2 electrons. So you could do this with every ion across the periodic table. One thing to keep in mind, and I would write this down and keep it in your head because it'll make more sense as we go along. These elemental ions, they want to take on the electron configuration of their nearest noble gas. I want you to start thinking about that and working that into your mind. They're going to want to take on the electron configuration of their nearest noble gas. So that brings us to ionic bonding. An ionic bond is not going to be like the covalent bond. We're not looking at sharing electrons here. Usually what happens is you're going to have two atoms come close to each other, and one atom will take an electron from the other atom. You see this happening on the top here. Atom A is actually giving off an electron to atom B, and as you see, atom B takes the electron and becomes negatively charged and leaves A positively charged. And then what causes the bond is the electrostatic attraction between the positive and negative charges. That electrostatic force of attraction is governed by Coulomb's law, which you see here. So the electric force binding the two ions is going to be K, which is the Coulombic constant. Q1, Q2. So Q in physics is charge. So what, +1, +2, so that's your charge. Charge of ion 1, charge of ion 2, and R is the distance separating the two ions. So if you had an ion here and an ion here, you're really going to go from the center of mass of the ion to the center of mass of the ion. This is your value R, the distance between the two ions. But it's just, you're not really going to be calculating this. I just want you to, I want you to know where electrostatic force comes from, because you could be asked this in definitions, but it's Coulomb's law is what will be dictating the strength of ionic bonding. You want to make sure you're getting the basic idea of how Coulomb's law works, because you will need to think about it again when we get to judging lattice energies. So one thing, let's start talking about how covalent and ionic bonding occurs. So ionic bonding occurs between metals and nonmetals on the periodic table. Let's see, do we put it up here? Covalent bonding. Here, covalent bonding occurs between nonmetal atoms. So two atoms have to be nonmetals for covalent bonding to occur. Ionic bonding is going to occur between metals and nonmetals. And as I said, one of the atoms will usually take an electron from the other. And one of the big reasons for that is going to be electronegativity, which, again, another term for you to get into your head. Electronegativity is how strongly an atom pulls on electrons. And so here you see sodium and chlorine. Chlorine is much more electronegative than sodium, so it's going to pull that electron off sodium and pull that electron towards itself. That's going to leave sodium as a positive, chloride now as a minus, because chlorine becomes the anion, so it becomes chloride. And so what you get here now is an electrostatic attraction between the sodium ion and the chloride ion, and you get sodium chloride. And we know that is common table salt. So this is the essence of an ionic bond. So let's start thinking about the periodic table. We need to know how to look at this and how to take it apart. The periods are the individual rows. The rows are going to represent the principal energy shells, the quantum levels that are available to an atom. So so we're going to get into this more deeply as we go along. Start thinking about this in your head. Like you're going to, so you see here you have your S block, D block, P block. And so the way this is going to work is your very first row here is 1s. Well, nope, there's not a 1p. We'll talk about that later. Your second row is 2s, so now you're in a higher energy cell, 2p. And row 3 is 3s, 3p, and so on and so forth. And we'll get into this pretty extensively with electron configurations. But that's the first thing rows are telling you. The second thing rows are telling you is they're giving you predictable shifts in chemical behavior. So like, for example, as I go left to right across the row, electronegativity increases. So for example, fluorine is the most electronegative element on the periodic table because electronegativity increases to the right. So up and to the right. Let's just do this. Electronegativity increases as you go up and as you go to the right. So this is also what periods are telling you, is this shifting in chemical behavior. But remember, the periods are your rows. Groups. Groups, of course, are going to be your individual columns. So here you see you have columns 1 through 18. Sometimes you're going to come across a periodic table that is going to do like 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So A, of course, your main group elements. So you can use columns 1 through 18, or you can use your A and then like your 1B, 2B, so on and so forth. You can use that system. It doesn't really matter. It just depends on the periodic table you're looking at. I just want to make sure you realize that, for example, column 17 is the same thing as column 7A. It's really just on how you look at it. So these groups are going to put atoms together that have very similar chemical behavior, valence electron structure, ionic properties. There's also a thing called families. Families can be synonymous with groups. So a family, like this first column is a family, and we'll talk about that. But families can also be more general. So for example, there's a family. That family is the transition metals. So families can be more generalized. Also, lanthanides are a family, actinides are a family. But you're going to want to keep in mind that your groups are your columns and your periods are your rows. Uh, Read through the stuff we're talking about here a couple of times. Some of it won't make sense yet, but I want you to have it in your head as we get to newer stuff later on. Something you're going to have to think about is the identifications of certain families on the periodic table. So many standardized exams will expect you to know this. I'll expect you to know this. So your families, for example, your group 1, so that's your first column. Those are your alkali metals. Group 2, those are your alkaline earth metals. We're going to jump over to group 16. Well, there's I call these chalcogens. There's some debate on how to say that, but there's a spelling for it. Here, group 17, those are halogens. You're going to make sure you know those. Group 18, those are your noble gases. So you'll see these names show up. So, for example, here, hydrohalic acids. Later on, I'm going to ask you about hydrohalic acids. And so you say, okay, well, how do I pick that apart? Okay, well, I see halic. Halic has the root in it for halogen. So hydrohalic acids are going to be acids that are combinations of halogens and hydrogens. So, for example, hydrochloric acid is a hydrohalic acid. You're also going to want to make sure you're thinking about different parts of the periodic table. So if you look here, these orange atoms, at least on this periodic table, those are your nonmetals. That is, well, then of course there's hydrogen up here. Those are where you're going to get your covalent bonding. So if you have nitrogen bonded to oxygen, that's going to be covalent. Carbon bonded to chlorine, that's going to be covalent. So again, your covalent bonding is non-metal bonding versus your ionic. So if I have nitrogen and sodium, that's a metal bonded with a no with a non-metal. So that's going to be ionic. So look at where your atoms are coming from on the periodic table, and that can help quite a bit. For the time being, we're really going to leave, so this like little stair step pattern here, those are your metalloids. We're really going to leave those alone because they can have variable properties. But then otherwise, when you're thinking about groups on the periodic table, of course, you can see the first two columns here. Then you see this section over here. Those two sections, the raised sections, are called main group elements. And then, of course, your little block, the B block in here, are your transition metals. So yeah, start working on the names of those individual groups. That'll definitely show up on exams and in quizzes. Now let's start talking about ionic charges as we look at the periodic table. Okay, so you you're going to have common charge and variable charge ions. You can see that here. Uh, and you can really tell what you're going to have based off its position on the periodic table. The way ions work is your column one. These will become ions with a +1 charge. Column two, these will become ions with a +2 charge. Now we're going to kind of stop there. Some of these in column 13, you notice we skipped the transition metals. There's a reason for that. So I'm just counting across the main group elements. So you see we have one, two, several of these in group 13 will be a +3. In particular, aluminum. As you'll see later, you're going to be tempted to name it differently, but aluminum is a common charge ion at a +3. Now we want to go over to the right and start going backwards. Your group 17 will take on charges of -1. Group 16 will take on charges of a -2. And your group 15 will predominantly take on a -3. It starts to change a bit as we get down to your your metalloid antimony and your metal bismuth. Those can vary a little bit, but we're not really going to go super deep into that. I just want you to know this general trend. So when you're looking at the periodic table and you say, "Oh, what charge will that ion have?" Well, you look at the periodic table, say, "Well, it's okay. Well, I have calcium. That's from column two, so that's going to be a +2 ion." Or I have sulfur. That's from group 16, so that's going to be a -2 ion. So make sure you're working through that and you understand that. Your variable charge ions, most of those are going to come from your transition metals. And what that's going to do is that's going to change how you name your compounds. So for example, let's take iron. This is called variable charge because, for example, you can have iron with a +2 charge, iron with a +3 charge. You could have, so that means that these elements their ions can take on multiple charges, and it's really going to be dependent on the chemical formula for you to calculate what that charge is. Okay, before we move on, there's some exceptions to this rule though, and I want you to mark these exceptions. This will be important when you're naming. Silver is an exception. Zinc is an exception. Cadmium is an exception. And then I told you about aluminum. So again, you're going to be tempted to think of aluminum as a variable charge because it's a metal. It is not. It is not a variable charge. So your exceptions, silver will always be a +1. Cadmium will always have a charge of a plus. Zinc will have a common charge of +2, and aluminum will have a common charge of +3. Again, I want you to know these exceptions because this is going to affect how you name compounds. Okay, so for each of the following atomic numbers, use the periodic table to write the formula and charge, or symbol and charge, for the simple ion that the element is most likely to form in ionic compounds. Okay, well, let's look at part A. Element 13, that's aluminum. Okay, aluminum is in group 13. We also know that aluminum is one of our common charge ions at a 3+. Let's see. B, element 34. So we look and we find selenium. Okay, so what charge will it take on? Well, it's in group 16. And so we know selenium will take on a -2 charge. Because again, that column, these are all going to be -2s. And now what name would this take? Okay, so aluminum, it's a cation, it's positive. So that's the aluminum ion. The selenium takes on a -2, so that's an anion, it's negative. So this becomes selenide ion. C 56. Oh, where's element 56? There. And of course, that's barium. Barium is in column 2. And we know as we're counting from left to right, we go +1, +2, +3. So barium being in column 2 has to be a +2. And again, it's positive. So you see it maintains its elemental name. It's just the barium ion. Well, what about D? D is element 7. That's nitrogen. And nitrogen being in column 15, remember we do -1, -2, -3. So nitrogen is a -3, and because it's an anion, it becomes the nitride ion. Or E, element 87. Okay, well, that is way down here. Francium. Now, again, it's column 1. So just like just like the rest of its group, francium will become a +1, and it's the francium ion. So it's a cation, doesn't change its name. Part F. Element 35. Well, that's right there. That's bromine. Okay, so bromine is in group 17, so we know that it has to become a -1. And it is the bromide ion. So you're going to get practice with this as you work through assignments, but just start thinking about the periodic table, what periods are, what groups are, what are the names of the various groups, and what are the charges of common ions on the periodic table. I still think the hardest part to get are these charges. So I would make sure you're learning this and you can pick out, well, what charge is that ion going to get based off its position on the periodic table. And again, make sure you know your exceptions to the charge rule. It's not really a rule, but still, your silver, cadmium, zinc, and aluminum. All right, now we're going to start talking about how to name compounds. Okay, yeah, we'll just take this in sections. So we're just going to start with the binary ionic compounds of type 1. So binary, two well, two atoms turn into their relative ions, come together to form a compound. So two different atoms, two different ions. And you're always going to get a cation anion combination. You might get, so down there you see BeCl2, and you may say, well, that's not two ions, that's three different ions. It's three ions total. Okay, yeah, but it's two different ions, beryllium and chloride. So you are going to have these present in different numbers because your ionic compound has to be neutral in charge. So you need enough positive and enough negative to add up to zero. So here, if you look at the BeCl2, that's beryllium chloride, and you're going to want to think about your periodic table. Beryllium is right there, so beryllium is a +2. Well, when I look at the periodic table, chloride is from group 17, so it's a -1. So I have beryllium that's a +2, chloride that's a -1. So what I'm going to need, beryllium's 2 plus 2 times chlorine's -1, that gives me 0 or a neutral charge. So that's why I have the 2 as a subscript on chlorine. The next one, Ki, potassium iodide, well, that one is just in a 1-to-1 ratio because if you look at the periodic table, the potassium ion is a +1, the iodide ion is a -1, so it's a +1 -1, you get 0 or neutral compound. Some of these can get a bit harder. Aluminum oxide. Okay, so we remember that aluminum is a +3. We see oxygen is in group 16, so it's a -2. Okay, well, how do these come together to equal 0? How do I combine a +3 and a -2? Well, I have to find the lowest common multiple. 3 and 2 both multiply into 6. So if I take 2 of my aluminums, that's going to be 3 times 2, that's a +6. 3 of my oxides, that's 3 times a -2, that's a -6. So 6 minus 6 is 0. So again, you're going to want to make sure you're getting these pluses and minuses together in a combination that equals 0. And here, the last one, we have Li3N, which is lithium nitride. Well, lithium is from group 1, so it's a +1. Nitrogen, or nitride, is from group 15, so it's a -3. I have to have 3 of the lithiums to neutralize the -3 charge on the nitride, so you get Li3N. So let's see here. Either name the compounds or write the formulas for the given names of the following ions. I gave you a bigger periodic table to work with. Hopefully you can see the names okay. Okay, so let's look at that first one, Rb2O. Okay, so I want to find these on the periodic table. Rb is right here, so that's rubidium. O is oxygen, that's right there. So I'm willing to bet this is rubidium oxide. Your chemical formulas for your ionic compounds will have the cation listed first. So your rubidium, of course, is going to be your cation. Oxide is your anion. You want to make sure your name is in the order of cation, anion. But if you're unsure, you can find them on the periodic table, and you can see rubidium is from column 1. And we also can make sure that this does add up to 0 or neutral compound. So rubidium is a +1. I have 2 of those, so that's going to be 2 times the +1 charge, or a total of 2. +2 is the charge. Oxide, it's in group 16, so it is a -2 charge. There's only one of them, so I get a -2. When I add these together, the 2 rubidiums, which is 2, minus oxygen, the plus the -2 from oxygen, equals 0. Let's see, maybe a more accurate, a better way to look at this. Say I'm adding the -2 of the oxygen to the +2 from the 2 rubidiums. And so another way you could look at this, each rubidium is a +1. So 2 rubidiums, 1 plus 1, plus the oxygen -2, that's 0. So yeah, this is a neutral compound. This is a good ionic compound. B, aluminum selenide. Okay, so I'm going to look. I'm going to say, okay, well, aluminum is right here, and I know from what I've been studying that aluminum is a 3 plus, so I'll just write a total of +3 as the charge. Selenide, so selenium's right there. Group 16, that's my -2 column. So all of the ions in that column are going to get going to get a charge of a -2. Your selenide will be a 2 minus. Okay, so here I have aluminum at a +3, selenide at a -2. Okay, well, how do I, again, this is going to be lowest common multiple. So I can make both of these meet at 6. Okay, so what I'm going to say, so if I do 2 times aluminum's +3 plus 3 times selenide's -2, that's going to give me 6 minus 6, or 0. So what I need is, and I did that 2 and 3 in a different color, so you can see what I need is Al2 Se3. Or let me make it even more clear. Al2 Se3. And if you're working some of these out in assignments, you don't necessarily have to do the step-by-step process that I've done, but I do want to see some of your logic on how you got to the proper answer. Because again, I could just use AI to look up the aluminum selenide molecular formula. I need to know you know how to find it. Okay, so part C. Yep, CAS. All right, where's CA? Ca is right here. That's calcium. This group is the +2 group, CaS. So then sulfur is right there. Sulfur's group is the -2 group. Well, this works out really nicely. So it's calcium, sulfide. Again, we do cation, anion in the name. It's also the same in the molecular formula, but you notice I have one of each. So that's going to be calcium is a 2 plus, sulfide is a 2 minus. And so what that's going to be is it's going to be 2 minus 2 equals 0. So those go to the calcium and the sulfide go together in a 1-to-1 ratio. That was part C. Part D, strontium fluoride. All right, let's find both of these on the periodic table. Okay, so fluoride is going to come from fluorine, so that's right there. That is my -1 column. Strontium, right here, same as calcium, that is my +2 column. Okay, so strontium is a 2 plus. Fluoride is a -1. Oops, we don't write 1, we just write minus. So I have to say, well, let me move this over a little bit so I can actually just write the numbers down. Okay, so how do I get this to come together as a neutral molecule? Well, I know that if I take strontium's 2, I have to subtract 1, that'll give me 0. Or 2 plus 2 times fluorine's -1 equals 0, which tells me that I have to have two fluorides. So my formula is going to be strontium fluoride. So those are your first set of ionic compounds. Binary ionic compounds type 2. Okay, these are going to be your variable charge ions. When you have variable charge ions, you have to include a Roman numeral in the name that tells you the charge on the cation. So there, your CrCl3. That is your chromium-3 chloride. Chromium can have multiple charges. So I have to include that chromium is a +3 in the name. So if you didn't know what the charge on chromium was, how do you start taking this apart? Well, chromium's going to have some charge X. I don't know what it is. Chloride has a -1. However, I have 3 chlorides. So my chloride in that compound ends up at a total charge of -3. And I have 1 chromium that has to neutralize that -3. So chromium has to be a chromium-3 ion. The next one you see titanium ox, so see TiO, you know that oxygen is a 2 minus. You have 1 titanium, 1 oxygen, so for the 1 titanium to cancel out the 1 oxygen, it has to be a +2, so titanium 2 oxide. Now the next one, your manganese 2 phosphide, this one's a little more difficult. Now, somehow that ended up as a subscript, but anyway, that's a 3 minus. So here we say, okay, so I look at the periodic table, I see where phosphide is. It is in group 15, the nitrogen group, so that means it's in the -3 column. Okay, so I automatically know phosphide, and I have 2 of them. Going to give me a total charge of -6. Great. So then I have 3 manganese. And I say, well, I have to have a +6 from the manganese. And then I say, what? So here, we'll put it over here too, +6. So then I say, what number times 3 will give me a +6? Well, that can only be +2. So this has to be, so it's going to be manganese 2 phosphide. These will take you a little bit of practice to get used to, but just, get working on them, keep going, and you will get used to them. Okay, so our next one, V2O5. V is vanadium. This one's again a little difficult. I have 5 oxygens. Each oxygen is a -2 based off the column that it's on the periodic table. Okay, well, 5 -2 is -10. Great. So whatever vanadium is, 2 of them has to be a +10. So that means that if two vanadiums equals a +10, vanadium has to be a +5. And so this is the vanadium 5 cation. So vanadium 5 oxide. And I forgot to write the oxide. Vanadium 5 oxide. Let's see. PDBr4. That was pretty straightforward. I look at the periodic table and I see that each bromine is a -1. 4 of them, the total is a -4. And I know that 1 palladium is going to neutralize those 4 bromides. So palladium has to be a +4. So that's palladium 4. I'm really forgetting the second name of these. And at least I stopped it with the nickel. So this is palladium 4 bromide. Let's see, NIP. So we want to look at this and say, okay, well, I know what the phosphide is. It is in the nitrogen group, so it is a -3. And there's 1 of them. So that's a -3. 1 nickel neutralizes that -3. So nickel has to be a +3. So this is nickel 3 phosphide. And then, of course, I put these 2 at the bottom because here's where the change comes in when you have your exceptions. So silver, let's go back up and look. Silver is a transition metal. So you're tempted to talk about it as a variable charge ion, but it's not. Silver is one of your exceptions, and it's a common charge at a +1. So here, of course, the chlorides based on they're group 17, so they're a -1. Silver is a +1. And so 1 silver and 1 chloride neutralize each other, but it's just the name is just silver chloride. You notice how I don't put the Roman numeral on the silver. That's because silver is a common charge ion. It's an exception to the rule, so you don't use the Roman numeral. The same with the zinc bromide. Remember, we said zinc is going to be, even though it's a transition metal, is going to be common at a +2. The bromides are halides. And there's another word for you. Your group 17, your halogens, their anions are called halides. So just like the anion takes on the IDE ending, like bromide, chloride, fluoride, you just take that IDE ending and slap it onto halogen, and you get halide. And these are your halide ions. And so we know that the halides are all -1. So I have the 2 bromides with the 1 zinc, but notice the name is just zinc bromide. There's no Roman numeral because zinc is a common charge, except common charge ion as a transition metal. It's an exception to this trend. So again, this will take some time to work through. You really want to make sure you know that you're picking out the difference between your common charge ions, which you will be able to tell based off their position on the periodic table, and then your exceptions, your silver, your cadmium, your zinc, and your aluminum. Otherwise, pretty much everything in here. There you go. Those are going to be variable charges. Your metals over here, like your tin, lead, so on and so forth, those are going to be variable charge ions. So you'll get used to it more as we go along, but make sure you see the difference in the naming between the variable charge and the common charge, and start working on breaking down these compounds so that you know why, for example, chromium 3 chloride is CrCl3, or let's see, lithium nitride is Li3N. Make sure you're working on why this is the way it is. Okay, so let's do the same thing we did above. Name the compounds or write the formulas for the following letters. So the first one, A. Now, Ti is titanium, and that is right there. That is going to be a variable charge ion, so we don't exactly know what its charge is yet. Okay, well, oxygens, they are group 16, so that is your -2 column. So I'm just going to write -1, -2, -3, +1, +2 to kind of help me out. Oxides are a -2, and I have two of them, so 2. So you have a total charge of -4 from the oxides, and one titanium has to neutralize that. So titanium has to be a 4 plus. So then what you're going to have is, now if you know the charge on it, titanium 4 oxide. So again, make sure you're showing me some kind of logic so that I know you're not just looking these up. Let's see, part B. Okay, mercury 1 selenide. All right, well, actually, this helps us because anytime you see that Roman numeral, you automatically know what the charge on the mercury is, or on your cation. That means your mercury is definitely a +1. You already know that based on the name. Selenide, where's it at? Well, it's right here. It's in the oxygen group, so it's a -2. Okay, so the way I make this neutral is to the selenide is -2. I'm going to have 1 plus 1 plus the -2 of the selenide. That's 0. So then I have to have 2 of the mercuries and 1 of the selenide. Hang on, did I do that right? Dun, 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 dun. Selenium. Yeah, I did. Okay. I wasn't paying attention when I made my notes. Okay, so it's going to be Hg2 selenide. Okay, so part C, silver iodide. Well, silver is one of my exceptions. So I already know that silver is a +1. It's the iodide. Okay, well, that's the -1 column, so column 17. So iodide is a -1. Okay, so that's already 1 plus a -1 equals 0. So silver iodide just goes together as silver AgI, and that's going to be your neutral compound. And part D, COS. Okay, yeah, where are these? Well, CO, that's cobalt. I don't really know what it is yet. S, sulfur. Okay, that one I know. So my COS Well, my sulfur is in the oxygen column, so it is a 2 minus, giving me a charge of -2 because there's only one of them. Well, cobalt, whatever X is, has one of them has to neutralize. Yeah, let's see. What's a good way to write this? Okay, so we could say 1 times X has to equal +2, X equals +2. So that means my cobalt is cobalt 2. So the name for this is, now you see you have the 2 of the cobalt plus the -2 of the selenide gives you 0. So the name of this is going to be cobalt 2. Oh, it's not selenide, it's sulfide. I'm dumb. Whoops. S is sulfur. It's not selenium, it's sulfur. Cobalt 2 sulfide. Okay, so when you're working through these, make sure you're showing me some logic and make sure that I can see all the pieces and that it's readable and I can follow it. But we'll finish up chapter 2 tomorrow and start getting into chapter 3. All righty, thank you.